Hello everyone, we're going to start something called the Aldol reaction, and it's right here, so please mark this down as your next reaction to learn. What's going on in this reaction is we have NaOH in water, and you see that we have this one molecule here, but actually we're reacting two of them. We often don't write a 2 there, but just get used to that idea that when you see this, this is reacting with another one like itself. So in this case, we have a mechanism for how this happens. And I could tell that there's 2 of them because there's double the number of carbons, right? So you know from before that we were taking the alpha hydrogens. And just as an aside, I think a lot of people are thinking back to the previous chapters where we would attack the carbonyl, but that's just going to give you a hydrate, and that's not going to go very far. So we also see evidence for a reaction where we take the alpha hydrogen, we make the enolate. Then, like I said, you could have another molecule like it because there's lots of these in solution. And we've got 2 centers of reactivity then. We have the negative charge on this alpha carbon, and we have the partial positive charge of the carbonyl. So here's our nucleophile, and here's our electrophile. So once we have this molecule, you can see it's going to get neutralized. It's going to pick up a hydrogen from water, and then it's going to become our final product. And this product is called an aldol product. I wonder if you guys can see why it's called that. It's due to its functional groups. We have an aldehyde and we have an alcohol. So that's why it's called aldol. Now it's could be that we had a ketone to start with. So this H over here could have been a carbon group. So it can actually work with ketones and aldehydes. We just call it aldol because we chose aldehyde, but you can also have ketones. So here's some practice with that. So pretend for each of these that you have NaOH and it's in water, and figure out what's the aldol product you would get from each one. Now these are a little tricky to draw out, so I'm going to do the first one and then have you guys practice the rest. I usually start with one of these molecules first, just exactly the way that it's written, so in its aldehyde or ketone form. So right here. And then I have to do a little bit of thinking back to the mechanism. Remember, this became a nucleophile at its alpha carbon. So I'm going to try to find that alpha carbon. I guess it's right here. And that's where I'm going to have a new bond form to another one of these aldehydes. So the new bond in this case, the example we did was from the alpha carbon here to the carbonyl carbon there. So it's actually this bond right here is the new bond. So we're always going to get a new bond in these reactions. It's a great way of making a carbon-carbon bond. So here's where that new carbon-carbon bond would be between this molecule and another one of these. And in blue, I'll show the second one. So we know that the enolate of one will attack the carbonyl of the other. So here's where the enolate is, the alpha carbon. This is the nucleophile of this one after reaction with NaOH. And then it's going to attack the carbonyl of another aldehyde like itself. So there is what used to be the carbonyl. That's right here. That's what I'm drawing right here. Okay, so once we have that, then I'm going to draw the rest of this aldehyde. So carbonyl, then 1, 2, 3, 3 carbons, 1, 2, 3, and then the ring. And notice you could have this is going to be negatively charged because the alpha carbon of 1 attacked the carbonyl, and then those pi electrons went up to this O. And then after water workup or dilute acid, we're going to have this be protonated. So here's something for you to think about. You have the alpha carbon of one aldehyde attack the carbonyl of the other. And this is now going to be a beta hydroxyaldehyde or ketone if you start with a ketone. Okay, so it's always that the OH group is going to be beta to the carbonyl group that's remaining, alpha beta. All right, so go ahead and use those and use the mechanism that we did up here and do the rest of these here, and I'll check with you in a few minutes. All right, so here we are with these, and what I did was first in purple, I drew the original molecule, and then I pictured the enolate ion right here on this carbon attacking the carbonyl carbon of the next molecule like itself, and putting the OH there, making sure this is alpha, beta, that's my new bond, and the beta has a hydroxy group. So here's my new bond right there. And making sure the hydroxyl group is beta, meaning it's alpha, beta to this carbonyl group. Then over here, same thing. So new bond, alpha, beta to the original carbonyl, and I have a beta hydroxy group and the rest of the aldehyde. And here as well, alpha is here, beta here, that's my new bond, connecting the two molecules together, and a beta hydroxy. Okay, so these are called aldol addition products. So a couple of questions for you to think about. Number one, when we're treating 2,2-dimethylbutanol with NaOH, we don't see an aldol reaction. So why is that? So our first step is we take NaOH and we attack an alpha hydrogen and we make the enolate. And do you guys see the problem with that in this molecule? There is no alpha hydrogen. These are methyl groups. So there is no way to make the enolate. And remember, that's not the acidic hydrogen. So there's going to be no aldol reaction. So probably the best we can do with this is the OH might attack here and we might get some hydrate, but that's about it. So no aldol reaction. No reaction at the alpha carbon. Now let's look at the next one. C4 alcohols treated with PCC to make an aldehyde. And that aldehyde has 3 signals in the proton NMR. So what is the aldol product? And so we'll need to know what the aldehyde and then what the alcohol was. So we have a C4 alcohol, and there's several options here. I recommend you look at all the different 4-carbon alcohols you could have, see which ones get oxidized to make aldehydes, and then of those evaluate how many NMR signals you would get. So here's one such alcohol. Why don't you guys think of the other ones and think about which ones would produce aldehydes, and then look at what you would expect in the NMR. Let's go ahead and pause it and see if you can figure that out. Okay, it doesn't take long before you realize that some of these alcohols aren't going to give you aldehydes. So like this one is not going to give you an aldehyde, it's going to give you a ketone. So there's really no point in drawing out all the alcohols. Let's just start drawing out all the aldehydes with 4 carbons. And you'll see there's only 2 such aldehydes. You can either have a straight chain of 4, or you could have this sort of isopropyl group on this aldehyde. Okay, so of these 2 aldehydes then, which come from these alcohols here and here, then you're going to have 4 signals from the aldehyde hydrogen, 1 here, here, and here, alpha, beta, gamma. So that's 4 signals. And for this aldehyde, you're going to have the aldehyde and the alpha and the beta. So because the 2 betas are the same or equivalent. So that's only 3 signals. So the aldehyde that we want is this one right here. And then we need to predict the aldol from that aldehyde. So the aldol will be that aldehyde, and then that's bonded to another molecule like it with a beta hydroxy group. Okay, so that will be my aldol product, alpha, beta, hydroxy, and we see the isopropyl group here for both of these. All right, so that brings us to this point of retrosynthetic analysis. Let's say we have an aldol product and we want to work backwards and say, what are the 2 aldehydes that I must have started with, or ketones? So usually what we do is we look at the new bond that had formed, which is the alpha beta, the bond between the alpha and the beta carbon. So that was my new bond, so I just break that in half and I should release the molecules I started with. So I probably started with something like this, but see how the carbonyl is intact. So that means that that did not react. It was the alpha carbon that reacted. So this piece of it was my nucleophile. And so that's the nucleophile I'm imagining is the enolate ion. That means this came from a molecule where there was an H there. So I'm basically just stepping it back in time to what I must have started with. Now let's look at the other half. The other half of the aldol product is my beta hydroxy group. So I'm going to step that back and say, oh, that came from a carbon here being electropositive in some way, which means that the sort of the glue between these 2 synthons or molecular pieces was the negative positive interaction there. So this positive came from the carbonyl oxygen, right? The carbonyl functional group, a C double bond O. So that COH came from a C double bond O. And here, that's where you see that it must have been partial positive here. And so I'm sort of picturing that this hydroxy group came from a carbonyl eventually. And this right here, this alpha carbon, was my nucleophile. It was where I had negative charge. And that's how these two molecules came together. Okay, so doing that, let's think of taking each of these and working backwards. This is called retrosynthetic analysis, or you could think of this as a retroaldol, where we go backwards in the aldol reaction. So we have our alpha carbon and our beta carbon. That's where our new bond was, formed between an alpha and a beta carbon. This piece must have been the nucleophile, and the alpha carbon here attacked this carbon here. So that means that my original aldehyde is exactly this, and it attacked another one like itself, because you'll see 1, 2, 3, 4, 1, 2, 3, 4. They're both actually the same aldehyde. It's just that one was the nucleophile and one was the electrophile. So the single molecule, which is answering this question, is this one, okay? So I'd like you to go through each of these and figure out what was the aldehyde you started with. All right, so for this one, we break the bond here between alpha and beta. That's where the new bond was. And so the single molecule that the aldol was based on is this one right here. And same thing over here. My new bond was right here between the alpha and the beta carbon. And so the molecule that was used was this one right here. And same thing here, but in this one it's a little tricky because it's actually still attached going all the way around this way. So it turns out this is all one molecule and it attacked itself. So the molecule you get actually looks like this. So it's actually a dialdehyde molecule where this alpha carbon attacked itself and became a hydroxy group there. So that's called an intramolecular aldol because it's happening within the same molecule. So why can't any of these undergo an aldol reaction? If you look at the alpha carbons, you'll realize that they do not have alpha hydrogens. So there are no alpha hydrogens or even an alpha carbon in this case right here. No alpha hydrogen on any of these to allow for enolate formation. All right, and once we have the basic idea of aldol down, now we can start talking about reacting different aldehydes or ketones with each other. So here's an example of what we call a mixed or crossed aldol reaction. And that's where we have different aldehydes or ketones. So for example, I have an aldehyde and a propanal here, acetaldehyde, propanal, and they're going to make 4 different possible products. You might ask, well, how is that? Well, don't they just react one here and one there? Yes, but they can also react with themselves. So acetaldehyde could react with itself, propanal could react with itself, and then acetaldehyde could be the nucleophile attacking propanal, or propanal could be the nucleophile attacking acetaldehyde. So you have all these different possibilities. So let's work through those. So first, let's do the aldol products where acetaldehyde reacts with itself and propanal reacts with itself. Then we'll get 2 aldol products at least. Now I want to think about how these might react with each other. So for example, maybe the OH group, OH hydroxide, could take this alpha hydrogen over here and make an enolate there. And then once I make that enolate, then maybe acetaldehyde could use the carbonyl of the propanal and attack that. So let's see what product we would get then. All right, so here's my acetaldehyde with its 2 carbon unit right here, and the alpha carbon of 1 is attacking the carbonyl of my propanal, which has 3 carbons in it. So there's my aldol product in that situation where this is the nucleophile and this is the electrophile. Now let's reverse the roles. Let's say that this hydroxy group took the hydroxide ion, took this hydrogen. This becomes my nucleophilic carbon and that attacks here. What would my aldol product be then? All right, so this is what I get then. So my acetaldehydes are all in blue, my propanals are in purple, so that you could see what's going on here. Acetaldehyde reacted with itself, one of them being a nucleophile for the other being an electrophile. Same thing with propanal reacting with itself. Then I could have a mixture. where one's the nucleophile and this is the electrophile. This was now the nucleophile, this is now the electrophile. So let's try practicing all that. And these are working backwards now. So what are the reagents you need to produce these mixed aldols? Or maybe they're not mixed, I'm not sure. We'll have to find out. Okay, so let's take A. We're going to do the same thing we did before here, but instead of getting the same aldehydes or ketones, we might get different ones. So let's see what happens here. Remember, the key to doing a retro aldol is to find your alpha beta bond between alpha and beta, which is right here. And when I cleave that, we're going to see what the two starting materials must have been. Okay, so in this case, this was a ketone, all right? So it's this ketone right here. And then the ketone was the nucleophile attacking the carbonyl of this one carbon aldehyde. So let's draw what that aldehyde was. So that one aldehyde was here. So this aldehyde and this ketone here reacted together to form this aldol product. Okay, so for each of these, I'd like you to draw out the two reactants you need to make these products. And go ahead and give these a try. All right, so for this one, part B, I had a split right here between the alpha and beta. That was my new bond. So I have cyclohexanone attacking this aldehyde right here. For the next one, I did the same thing, split it, the cyclohexanone, and is now attacking this ketone. Here for part D, cyclopentanone is attacking benzaldehyde. And right here, this is acetophenone attacking acetaldehyde. Now, so far we've been using a lot of aldehydes, and the reason why is because the energy profiles for aldehydes reacting is much lower energy than for ketones reacting, and that's for several reasons. One reason is that when you have the alpha carbon attack, the aldehydes are less sterically hindered as electrophiles. So aldehydes make really great electrophiles for that reason. We also know aldehydes are more reactive at the carbonyl carbon because there's less electron donating groups. So for both steric and electronic factors, aldehydes are greater electrophiles than ketones are. So for aldehydes, this carbon is more electrophilic, meaning more partial positive for attack, and also less steric hindrance. So in a mixed reaction where you have an aldehyde and a ketone, then you want it such that the aldehyde is always a better electrophile. So it, or let's say that it's usually, depending on its other R group as well, but aldehydes tend to be pretty good here because they're more electrophilic than ketones, which have more electron donating groups attached. So the two possible ones that we might get are the ones where this is the electrophile. So let's figure that out. Which of these are aldol products in which this acetaldehyde is the electrophile? So you can imagine when this attacks itself, this is the electrophile, but also the nucleophile. So there's that one right here. And then it's also possible that the ketone is the nucleophile and it attacks this as the electrophile. So in that case, we would have this one here. Okay, and what my key is that I'm looking for this acetaldehyde that was attacked either by itself or by the ketone. But as long as this is the electrophile, it's more likely to be produced than these other products. Now these will also be produced, but they'll be our minor products. So these are the mixed aldol reactions then, and I want you to use that concept that the electrophile is better off when it's the aldehyde. So go ahead and show me the most likely products, so not all the ones possible, but just the more likely ones in which that's the case. All right, so for each of these, I noticed at the beginning anyway that there were a lot of aldehydes without any alpha carbons. So there's no circumstance this can ever be the nucleophile. So this one has to be the nucleophile, and it's going to prefer to attack the benzaldehyde rather than itself because it's a ketone itself. So then I'll get this product where there's my benzaldehyde electrophile. Here's my acetone nucleophile. All right, so this attacked here. Picture the mechanism whenever you can. All right, for this one, same thing. This can only be the electrophile because there's no alpha carbons. So this alpha carbon's the only one available to be a nucleophile. And then it probably attacks here rather than another one like itself, simply because This one has less R groups, so it's going to be even more electrophilic and even less steric hindrance than it attacking itself. So I've shown that right here. There's that formaldehyde attached on. Here I have, and that's not to say this can't attack itself. You definitely will get some of that product as well. It's just that this will be the major product. Here, this cannot be the nucleophile, only the electrophile. So this will be the nucleophile that attacks here, and it prefers attacking this because it's an aldehyde, not itself, which is a ketone. So there's the benzaldehyde. Okay, here we have lots of options. We have 4 possible products, but we only want the major product. So this will be either the nucleophile attacking itself, but this is a ketone. So this could be the nucleophile attacking this electrophile, but this is also could be the nucleophile because it has alpha hydrogens. And so if I have this be the nucleophile, then it might attack itself. And that's actually favored because we have less steric hindrance than, see, all these methyl groups and this phenyl group. So it's going to be more likely to attack itself. And same thing here as well. It's going to be more likely to attack itself because even though this is an aldehyde, this phenyl is still some steric bulk. Okay, it's still carrying some baggage. So this will probably prefer attacking itself instead. And so the reason why it preferred to attack itself is because acetaldehyde is both a better nucleophile and electrophile compared to benzaldehyde. Benzaldehyde has no alpha hydrogens, so it can't even be a nucleophile. But in terms of being an electrophile, it's got this steric hindrance right here. So this will prefer to be formed over product B for that reason. So less steric hindrance. And then also you might think about the electron withdrawing factor or donating factor. The more electropositive this is, the better. They're both aldehydes, so they're better than ketones, but compared to each other, we've got this alkyl group here, which is slightly donating, but then we also have this ring here, which is donating by resonance. You could almost picture the resonance structures where you donate those pi electrons into this. So it's possible that this might be a little bit more electron donating. So now let's say that there's 2 procedures for how we can get more product B. We can control factors experimentally to make product B more favored. So read through each of these procedures and see if you could figure out in which situation you would be able to control it so that there was more product B. So let's read these together actually. Procedure X says take a small amount of benzaldehyde to acetaldehyde with base. So I'm going to picture in a test tube. I have acetaldehyde and base, and I'm going to add a small amount of benzaldehyde to that. And in procedure Y, I'm going to do the opposite. Instead of adding a small amount of benzaldehyde to my acetaldehyde and base, I'm going to do it the other way around. Why don't you give that some thought and see if you can predict, is it going to be X or Y? So it turns out that if you have base mixed with acetaldehyde, it has alpha hydrogens to become a nucleophile. So what's going to happen here is this is going to become enolate right away. And if something is present for this to react, it's going to go ahead and react. So it's actually present to react with itself. So what I'm going to say here is that if there's base here with acetaldehyde, acetaldehyde's going to have a party. It's going to become enolate, and then it's going to have other acetaldehydes to react itself with. And then we're going to make more product A, probably before we even have a chance to add benzaldehyde. But look at procedure Y. This has no alpha hydrogen, so it can't really start to make enolate. So it's just sort of waiting, and as we add this dropwise, we're only adding a little bit of this, such that this will react to make enolate here in limited quantities, and the only thing possible for it to react with then is benzaldehyde. So here we're controlling the situation so that there's a little bit of enolate getting formed at a time, and that it's more likely to react with benzaldehyde, which will be in a greater concentration. Remember, because I'm only adding this dropwise. Okay, so procedure Y is going to help me to produce product B over product A. The last part of this lesson is to look at what happens if we add heat. So heat is usually this delta sign here. And so we're doing an aldol. I can tell we're doing aldol because I have an aldehyde or ketone and I have NaOH in solution. But now when I add heat, I get this pi bond. So this is called condensation, and notice that the OH group is no longer here. In fact, the OH turns into water somehow. So condensation is when you remove water or water is a product. So let's talk about the mechanism for that. And we'll start out with just the aldol addition. So go ahead and do the aldol reaction that we did before with the OH group that's beta. So here's what I have so far is I have my aldol addition. I make my enolate. Enolate attacks another one of these. I get this aldol addition product that's neutralized. And now I want to try to figure out how do I go from here to condensation if heat is involved. Now in this, we're given a clue that the enolate forms, then the leaving group leaves. So this is called E1CB. So it's actually not an E2 mechanism. It's technically an E1. CB means conjugate base. So what I want to do here is I'm going to form an enolate from this product. So the only enolate that I can form is right here. Okay, so let's say that I have an OH hydroxide ion come in, grab this, make an enolate here. Then what's happening here is this becomes the conjugate base of this, and this is what ultimately kicks out the hydroxyl group. And since we're in basic conditions, it's okay to have a hydroxyl as a leaving group. Okay, so that is it. That's how we get our product here at the final product, which I'll draw an arrow to that. Or you can just draw it right here if you want. Okay, and that's because we have heat involved. All right, and heat is driving reactions that there's going to be a strong entropy change. So as we make one molecule turn into two parts, that's going to help drive that reaction. So aldol condensation is when you have an aldol addition. So we had the same kind of reaction we did before. Here's our aldol addition. And then if you see heat, then you'll see that there's a way to get a pi bond there. And that's actually what was going on. A few pages back, we had the condensation here, but I forgot we didn't cover that yet, so it's got snuck in there. All right, and sometimes condensation just happens even without a lot of heat. You might not have to heat up your solution. Maybe there's a lot of resonance or conjugation that promotes that as well. So sometimes you see condensation even without the heat. For our purposes, I'll try to include it. So let's say that we have aldol addition of this, and then it does a condensation. What would that product be? So let's do one of these together. We're just going to make the aldol product here. So I start with this, and then I do the beta hydroxy group, and then I do the rest of it. All right, and then instead of that hydroxy group, I'm going to think about the enolate forming at the alpha carbon and releasing the OH of the beta. Okay, so I'm picturing this going on, the alpha enolate, and then it comes in and it releases. And you'll notice that aldol condensation is always conjugated. It's always at the alpha beta. It's called an alpha beta unsaturated carbonyl. So that's how we get those. So you want to make sure your pi bond is alpha beta. All right, go ahead and give these a try, and we'll check our answers. All right, so for each of these, you do need to consider possible stereoisomers as well. I didn't mention that before, but thought maybe you might see that. We want them to be a trans or Z opposite E isomers whenever possible. So this large group will not want to be on the same side as this group, for example. So same thing with this. You'll want this isomer here, these isomers here. This one is symmetrical. This one symmetrical. So yeah, just think about that when you work on these, okay? And then the other thing is, common mistake is to lose track of your carbons. So it's probably a good idea just to count, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, whoopsie, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6. See, I'm missing a carbon right here. So just want to make sure that you have all your carbons, because it's very easy to make that mistake, as I just did. And this one as well. You want to make sure, because it can be quite a visual illusion, optical illusion here. So 1, 2, and then the ring, 1, 2, and then the ring. So making that mistake several times here. So just be very aware of that. All right, now it's your turn to maybe think about what are the starting materials that you use to make these Aldol condensation products. Go ahead and give these a try. Okay, and so for each of these, it turned out that they're symmetrical, so meaning that I had one aldehyde that it ended up attacking another aldehyde like itself. So there's really only one starting aldehyde or ketone. They're not mixed products after all. And then this here is tricky. CHO is the abbreviation for aldehyde, so go ahead and draw that in, and then you'll see that this is where the beta hydroxy group was, and so I sliced down the alpha beta, and that's how I get my aldehyde released. And here's the aldehyde released from there. It turns out to be the same as the one that got attacked. Okay, here's a problem on intramolecular aldol. See if you can figure out how this might close into a ring based on an enolate forming either here or here or here or here, any of the alpha positions. But remember, you always want to maximize the ring size to about 5 or 6 membered rings have the least ring strain. So see what you would get as a product if an enolate formed and it attacked itself in an intramolecular aldol. Okay, so for this one, in order to maximize my ring size, I need to pick one of these end carbons to make my enolate, and then it will attack the carbonyl opposing it. So one will attack 5, or if you made your enolate here at 6, it would attack 2. Either way, you're going to have a 1, 2, 3, 4, 5 membered ring, and I numbered them just to make sure. 1, 2, 3, 4, 5, 6. And remember, carbon 1 attacked carbon 5. That became an OH group, and it has carbon 6 hanging off of it. And once I have that aldol addition product, then I picture the alpha-beta condensation going on like that. And then you can also have aldol reactions occur in acidic solution, not just basic. So this is also possible, and just involves a totally different kind of mechanism. So see if you guys can figure out how to do this acid catalyzed reaction. And it's going to have to go through an enol instead of an enolate. Enolate ion we make when we're in basic solution. In acidic solution, the nucleophile will be the enol. Okay, so go ahead and give that a try. So for this one, we've got protonation first to activate this, and then we're going to do our enolization or tautomerization here. So we've got a keto form going into the enol form. And once in the enol, this will become our nucleophile here by bringing the electrons down. And from the alpha carbon, we attack the carbonyl of another activated one here. Okay, once I have that, then this part becomes this one, and I just rotated it, and then I have the alpha hydrogen of, sorry, I have this guy here is now what this becomes. Okay, and then at the alpha position, it attacked this one here. So this OH here becomes this OH down here. And then I can have condensation happen here, and I can have deprotonation here. So you'll end up with this molecule, but you could have different stereoisomers. These could be on the same side, or they could be on opposite sides. So one thing I didn't show. And it depends on what the R groups are, just to know which one's your major and minor. And next time we'll cover Claisen condensation.